and ask if there are any questions on what we talked about last time.
I have some questions from the notes, but I can ask later.
Okay, that's fine. Yeah, I'll stick around again after class today, so you can ask whatever questions you want then. So remember last time we had written an expression for the delta function, that delta of x minus a is 1 over 2 pi times an integral from minus infinity to infinity over a variable k, so integral dk, of e to the I k x minus a. Now, both sides of this equation are technically ill-defined because the delta function doesn't exist really as a function. It's something that we sort of pretend is a function, even though it's not. And on the right-hand side, that integral doesn't actually converge. So one way to make sense of this is to do what's called regulation of it. So we can regulate by introducing yet another parameter that I'm going to call capital delta. And capital delta is something that we're going to take to 0 in the end. But what we're going to do before that is we're going to sort of define delta x minus a as the limit as capital delta goes to 0 of the same integral. But now we're going to insert a factor of e to the minus k squared of delta squared inside the integral. So what does that do? If delta is going to 0, then this thing is just going to go to 1, and so we haven't really done anything. But for any non-zero delta, what this factor does is it makes the integral converge. So we can sort of label this as a convergence factor. And then by taking the limit, it goes away. But before taking the limit, it's useful because now the integral does exist. It's a finite integral. And so we can think of the delta function as the limit as capital delta goes to 0 of, when you do the whole integral, it turns out to be the following: exponential of minus x minus a squared over 2 delta squared, all divided by square root of 2 pi times delta. So if you graph this, this looks like one of the things we talked about last time. Here's, as a function of x, I'm graphing this function, and there's the point A. And then the shape of this is a Gaussian that's tall and skinny. Okay, and the height of the Gaussian is proportional to 1 over the small number delta, and the width of the Gaussian is proportional to delta itself. Okay, so in that way, we can think of the delta function as this limit of very tall, very skinny functions that have support only near x equals a. Okay, so also last time, we had introduced a one-to-one correspondence between kets and wave functions. So if we had a ket that we call psi, we can associate with that a wave function, psi of x. They're not equal to each other. They're associated. That's what the double arrow means. And the relationship between them is that psi of x is, by definition, the inner product of the ket of the bra x with the ket psi. So now we can ask the question, given psi of x, so if I hand you a wave function, what ket would correspond to its derivative? 'Cause So what ket corresponds to d psi by dx? And so one way to answer that question is to just give it a name. So let's call it d acting on the original ket psi. Okay, so d acting on the original ket psi is defined to be the ket d psi by dx. Okay, and so what that means is that the matrix element of x with d, the operator, psi, is equal to the inner product of x with this ket d psi by dx. Okay, and that's the function, the wave function d psi by dx. Okay, so now what should we do with this? When in doubt, our mantra is to use completeness. And so let's go ahead and do that. So in this case, completeness is going to take the form that if you take the integral from a to b of dx prime, x prime, x prime, that's equal to 1. That's saying if you sum over all positions x prime, you get 1. Okay, and we're going to insert that relation into the previous equation. Okay, so what do we get? First, let me write down the right-hand side. D psi by dx is equal to, now I'm going to write down my integral. Then I'm going to write down x and d psi by dx, but inside I'm inserting x prime, x prime. Okay, and oops, that's not what I meant to do. I meant to first put in the operator d. Then I'm going to insert my x prime, x prime. And then I'm going to put my psi. Okay, so I've just taken this equation right here with that, and I've inserted the completeness relation. And so this is equal to integral from a to b dx prime of psi x prime. That's the last factor here. And then I have x d x prime. So I've related this to the matrix element of the operator d, which is the derivative operator between two position eigenkets. Okay, so now I claim that that object, x d x prime, is equal to d by dx of the delta function x minus x prime, which, by the way, is also equal to minus the derivative with respect to x prime of the delta function. And the reason we know that is because this is a function only of x minus x prime, so a derivative with respect to x is the same thing as minus a derivative with respect to x prime. Okay, so let's check the claim. Okay, and so to do that, we take our d psi by dx expression, and we're going to plug in that matrix element to see if it works. So I have psi of x prime. The claim was this was d by dx of delta of x minus x prime. Okay, and now I notice that my derivative with respect to x, I can take outside of the integral sign, because the integral here is with respect to x prime, which is independent of x. So I can write my d by dx on the outside, and then I have an integral a to b dx prime psi of x prime delta x minus x prime. And the good thing is about this integral is by the definition of the delta function, that's nothing other than psi of x. Okay, and so that works. That's equal to d psi by dx the way it's supposed to, according to the left-hand side, And so that checks the claim that our matrix element of the derivative operator between x and x prime is actually equal to the derivative of the delta function. Okay, so what we did there is we learned something about this operator D that takes derivatives on wave functions. And now we can ask the question, is it a Hermitian operator? So is D Hermitian? And the answer is no. And so to prove that it's no, let's consider the matrix element of D dagger, the Hermitian conjugate. So if this were Hermitian, it should be the same thing. This should be x prime. This should be the same thing as xd x prime, but let's see if it is. So this is equal to the complex conjugate of x prime d x. So notice the strategy here is to relate d dagger to d, and we did that by writing this as a complex conjugate. That in turn is equal to d by dx prime of the delta function of x minus x prime, complex conjugate. But here we can ignore the complex conjugate because everything here is real, derivatives are real, and the delta function is real. So we can ignore just because everything's real. In general, you can't ignore complex conjugation, but here you can. And so this is minus d by dx of delta of x minus x prime, as we mentioned earlier, which is equal to minus x d x prime. So if this were Hermitian, it should have been positive x d x prime, but it came out to negative x d x prime. And so what we learn is that it's not Hermitian, it's anti-Hermitian. So D is not eligible to be an observable because observables, we said, had to be Hermitian, not anti-Hermitian. So that's bad news. But on the other hand, that means that if we just multiply this thing by either I or minus I or anything else like that has an I in it, it's going to be a Hermitian operator and it will be okay. So that motivates defining P to be minus I h bar times D. Now you could say, why did I choose minus I instead of positive I? And the answer to that will only become clear in a future lecture. But that's, for right now, that's just the definition. And the h bar here makes this thing have units of momentum. So this is, in fact, the momentum operator. Although, again, it's not clear why it shouldn't be, for example, minus 17 I h bar d. But we will, again, in a future lecture, we'll figure out that this is exactly the right thing to be the momentum. Okay, and this is Hermitian. And at least it has the right units for now. So the units, if you put in the units of h bar and the units of a derivative with respect to x, it has units of momentum. Okay, so now if I act with this p on a ket psi, that's equal to minus I h bar times the ket that I would get by taking the derivative of the wave function and finding the associated ket. Okay, so that's how it acts. And so if I have a function f of x, which is a wave function, and another wave function, g of x, I could have called these psi1 and psi2, it doesn't matter. Try to mix up notation here and there just for fun. Then, if I look at the matrix element of G, the ket, G the bra, P the operator, F the ket, then by completeness, this is the integral from a to b dx of g of x, x pf. Okay, so here, as usual, we've used completeness. Okay, and then this we can write as minus I h bar, integral from a to b, g of x complex conjugate. That's from this inner product. And then this thing we learned is equal to, well, this is df by dx when I put in the minus I h bar that came about from the definition here. Okay, so now we can interchange the roles of G and F. So interchange G goes to F. And we learn just by replacing G with F and F with G everywhere that F P G is equal to minus I h bar, integral from a to b, dx f of x star dg by dx. So why are we doing this? The point is that we're not going to necessarily trust that this thing is really Hermitian. We seem to find that D was anti-Hermitian, and we multiplied by a minus I, which naively would make it Hermitian because the I will flip sign when we take the Hermitian conjugate. But because this is an infinite dimensional Hilbert space, it's a really good idea to make extra sure and to check. And so let's see what happens when we check the Hermitian nature of this thing. So to do that, what we're going to do is we're going to look at the complex conjugate of G, P, F, which according to the rules of taking adjoints is equal to F P dagger G. Now we're hoping that P dagger is equal to P, but let's find out. Okay, so now we just take the expressions that we've derived here, and we get F P dagger G minus F PG. Okay, that should be 0 if P is really a Hermitian operator, equals I h bar, integral from a to b, dx of G derivative of F star plus F star derivative with respect to x of G. Okay, and so now we can notice that this is a total derivative. This is the derivative with respect to x of G F star. And now we can use the fundamental theorem of calculus to integrate a total derivative and find out that this thing is not necessarily 0. It's actually I h bar F star B GB minus F star A GA. Okay, so our goal was to try to prove that the momentum operator was a Hermitian operator, which would make it an observable, but it didn't work. It came out to be something that looks like it's non-zero. So what that means is that despite our best intentions, the momentum operator is not Hermitian unless we impose some further constraints on the wave functions. Okay, so what can we impose? For P to be Hermitian, which is what we want, this must vanish. And there are several ways we can do that, but they all involve restricting the allowed wave functions. And the way we can restrict them is we can restrict them to those that satisfy f star of b, g of b, equals f star of a, g of a, at my two endpoints, the two places where that are the extrema of where the particle is going to be allowed. So this can be satisfied if, and here there are several ways. One is if I have periodic boundary conditions. So for example, my x, I said it was like a position coordinate, but it could actually be an angle. So for example, if x is equal to some angle theta, which is an angular coordinate, with a is 0, let's say, and b is 2 pi. So that means I go around a circle, and my wave functions, all of them, should satisfy psi of 0 is equal to psi of 2 pi, which kind of makes sense. Okay, so that works. But what if I don't want to restrict to a finite interval? What if I want my interval where the particle is allowed to live to be infinite? It can still be true if, for example, I'm talking only about bound states. So what's a bound state? So a bound state is, for example, I let A be minus infinity, and I let B be infinity, plus infinity. And I just require that the wave function at those 2 points vanishes. Okay, so that would work. But we're also going to want to talk about more general states that are not bound states, that vanish at infinity. Those are called unbound states, or sometimes called scattering states. So equals scattering. These are used to describe the particles that come from very far away and do some scattering and then go off to infinity again. And in general, they don't satisfy the condition necessary to have a Hermitian momentum operator. So don't satisfy in general. And so in a precise treatment, what you should do is replace them by wave functions that do satisfy this condition. So in a precise treatment, we should replace these by wave functions that approach 0, or at least some constant that doesn't depend on whether you're talking about the lower or upper limit of integration. Or perhaps a constant at very large distances. Otherwise, technically, momentum will not be unobservable. Okay, now, if you do all that, everything gets very complicated, and you have to write down in general, very complicated expressions in order to make progress. And then you do a lot of work, and you find out that actually things work out exactly as if you hadn't bothered with all of this in the first place. So it turns out that it's okay to treat other wave functions as idealizations, but you just need them to be finite at large distances.
Professor?
Yes, sure.
What is that?
Sorry, I didn't catch that. Sorry, I'm not hearing you.
I think your internet cut out a little bit.
That imply about the momentum? Right. Is that better?
Sorry, you cut out for a second. Yeah, can you repeat the question?
Yeah. Can you hear me better now?
Yes.
Okay. what does that imply about the momentum if mathematically we have to take all these steps to make it act like an observable
So
when I think you get what I'm saying.
yeah, so really it's not so much what it's telling us about the momentum operator, it's what it's telling us about the states or the wave functions. And it's telling us that technically we should not consider wave functions that extend off all the way to infinity. But what I'm getting at here is there's a way around this, and that is you could take the wave functions to extend out to the nearest star, or maybe 10 megaparsecs or something like that. And so as long as you restrict to wave functions that have some finite extent, by, for example, putting everything in a giant box that's half the size of the observable universe, then everything's fine, everything's mathematically well-defined. You'll have to do a lot of very complicated algebra and stuff to get everything to work, but in the end, it turns out everything works just as if you had ignored this problem, pretty much. I was just about to say the one thing that you must do in order to not run into problems, and that is that you need your wave functions to be finite at large distances.
So what exactly does that, why is it that it all works out?
So really it's just the fact that as long as my wave functions are constrained to some finite volume that, let's say it's the size of our solar system, it really doesn't matter to us very much if we're asking questions about what happens here on Earth, whether the wave function is doing something crazy once you get outside of Neptune's orbit or whether it doesn't, right? It's just sort of irrelevant what happens really far away. And so if you ignore this technical thing and don't worry about it, as long as the funny business is going on outside of Neptune's orbit, it's not going to have any practical effect on us here. That's sort of the heuristic reason. And then you can dress this up with all kinds of complicated mathematical distinctions with epsilons and deltas. But what I'm telling you is, from a practical point of view, it's kind of a waste of time to talk about. Just things that happen super far away aren't going to affect us.
Okay.
That's the general lesson. Okay.
Right.
But in order for that to be true, we just need this one thing. We need wave functions to be finite at large distances. Because otherwise, if I assume that my wave function is going to exponentially grow as we get out to Neptune's orbit, then bad things can happen and will happen in general.
Okay.
And one of the bad things is the momentum operator won't be Hermitian for that class of wave functions.
Right.
Okay.
Thank you.
Sure. All right, so we've listed ways that you can restrict the wave functions to make sure that momentum is a Hermitian operator. And now that it is, it's an observable, and so let's talk about its eigenvalue problem. So eigenvalue problem for momentum. And we're doing this all in one dimension, but at the end, we'll talk about how to generalize this to 3 dimensions, where actually generalizing it to 3 dimensions is pretty easy. So what's the eigenvalue problem for momentum? We have our momentum operator P. It's going to be acting on a ket little p, which is going to be our eigenket. And because it's an eigenvalue equation, that should be a number p multiplied by the ket p. Okay, so this capital P is our operator. The little p here as a ket is the eigenket. And this little p, the number, is the eigenvalue, which is going to be our momentum. Okay, and so this p is continuous, And so we have to impose Dirac orthonormality. Okay, and so what that means is instead of the inner product of P and P prime being a Kronecker delta, it's going to be a Dirac delta function, which means these things do not have finite norm. And so once again, they're not technically members of the Hilbert space. They're idealizations. And so if we then do completeness, it looks like this: minus infinity to infinity dp of pp is equal to the identity operator. Okay, so that's Dirac orthonormality and completeness for momentum. Okay, and so for every possible momentum, there is one of these kets, and they're labeled by the same thing as their eigenvalue. Okay, so now with this, we can define the momentum wave function. In the following way. So this is, I should say, for any ket psi. And it's defined to be psi tilde of p is equal to the inner product of the bra, the eigenbra for p with the ket psi, the state psi. So the tilde is just because we also had psi of x, which was x inner product with psi. So we just need some way to distinguish them, and the conventional thing usually is to just put a tilde on top of the function, because in general it's a different function. Okay, so now using completeness, we can learn the following. Suppose we have two kets, phi and psi, and we take their inner product. Completeness says this is integral minus infinity to infinity dp of phi tilde of p star psi tilde of p. So that what this equation is doing is telling us how to compute an inner product if we've been given the momentum wave functions for the two kets involved. All right, so now let's consider what is the position wave function of a momentum eigenstate. All right, or a momentum eigenket. Okay, so first let's give it a name. So we'll call it phi sub p, p is the momentum, of x. It's a function of x because it's a position wave function, but it's labeled by p, which is telling you which momentum you're talking about. And by definition, a position wave function is the inner product of the x position bra with the ket, which in this case is p, the momentum eigenket. And our goal here is to solve for this thing. So we now have all the information we need to be able to solve for it. And the way we're going to do that is we're going to consider the following matrix element, x with the momentum operator acting on the ket p. We're going to consider that because we know that p the operator acting on p the state is little p, and that's a number, so we can pull it out. And then that's equal to p times the thing we're trying to find. Okay, but also we have another way of writing it. Okay, and that is we can write it by using completeness. As usual, completeness comes to the rescue. This time it's completeness in x, So I'm going to write an integral minus infinity to infinity dx prime. I'm going to write down my x and my p, and then I'm going to insert my states x prime. Okay, and then this factor right here, that's phi p of x prime by definition. Okay, and this matrix element is equal to minus I h bar d by dx of x and x prime. That's using the definition of what the p operator does. And then we remember that x with x prime is delta of x minus x prime. Okay, so the whole thing, just cleaning up the mess a little bit, is equal to minus I h bar d by dx. I'm taking the derivative outside the integral sign. Minus infinity to infinity dx prime of delta x minus x prime, and then phi of p times x prime. So the magic thing that's happened is that now we're in a perfect form to be able to use the definition of the delta function, because when you integrate a delta function, you just replace x prime with x, and you have no integral left. And so this is equal to phi sub p of x, which is again the thing we're trying to find. And so what's happened is we've written down two expressions that are supposed to be the same, and we've learned a differential equation for the quantity we're trying to find. D by dx of phi p of x is equal to I p over h bar phi p of x. Okay, and that's a first order linear differential equation. And we know how to solve it. One way to solve it is just to guess the answer. So phi p of x is equal to an arbitrary constant, which is really a constant of integration, times e to the I px over h bar. Okay, so that's our solution. So let me make some remarks about this solution. Is first of all, this constant is arbitrary. It could be complex in general. It's arbitrary because both sides are proportional to phi p of x of our differential equation, and so it will just cancel out no matter what it is. The other comment is that our p here has to be real. And there's sort of two ways of thinking about why it's real. First of all, the eigenvalues of a Hermitian operator we learned are supposed to be real. But we also argued, not very rigorously, but argued anyway, that we can't have this thing blow up at very large distances. And if it were complex, then like I times something, then the exponential either at x goes to positive infinity or negative infinity would blow up. And we can't have that. Then p wouldn't be a Hermitian operator, we said. And so it's real so that phi p of x doesn't blow up as x goes to plus or minus infinity. Okay, oops, what happened there? Okay. So even though this constant c sub p is arbitrary, we can still solve for it if we demand that this wave function be normalized. And so to fix what c sub p is, we're going to consider the inner product of p prime with p for possibly two different momenta. Okay, so let's just do that. As you would probably guess by now, that's going to be just imposing completeness, this time completeness in x. So we're going to do an integral over all x, take our inner product, insert xx, Okay, so this is completeness in X. Okay, and then this is equal to minus infinity to infinity of dx of phi p prime of x star, phi p of x. Now we're going to plug in the boxed equation. This is equal to Cp prime complex conjugate, Cp, times an integral from minus infinity to infinity, dx of e to the I x p minus p prime divided by h bar. All right, so now the nice thing about this integral right here is that when we started out the lecture, we actually started with this integral up to some factors of 2 pi and h bar. If you look back, this turns out to be 2 pi h bar times the delta function of p minus p prime. That's what that integral was. And so this is equal to, just cleaning up the mess, Cp squared 2 pi h bar delta function. So one thing I did there is I said, oh, the delta function is only non-zero if p prime is equal to p anyway. So right here, I could take this p prime and replace it by p. Because if p is not equal to p prime, then the whole thing just vanishes anyway. And so it's 0 and it doesn't matter what it is. Okay? So we want this thing to be this delta function. And so what we really want is for this factor right here to be 1. So we're going to make this 1. In order to have Dirac orthonormality. And so a solution to that is to say that C sub p is 1 over square root of 2 pi h bar. Okay. That's one solution. I could have taken this and multiplied by any phase. That's an arbitrariness in the definition. There's no way around it except to just choose something, choose a solution. So it could multiply by any phase, it would still work. But why would you choose some weird phase when you could just choose this thing to be real and positive? And so that's what we're going to do. We're going to choose it to be real and positive. Okay, so now we can do some checks. One check we can do is check the matrix element or the inner product of x prime with x. How are we going to check it? Let's use completeness. Why not? That's what we always do. Minus infinity to infinity dp of x prime p px, right? And now this is equal to 1 over the square root of 2 pi h bar e to the minus I px over h bar, according to what we just learned. And similarly for that. And so the whole thing works out to 1 over 2 pi h bar minus infinity to infinity dx, or sorry, dp of e to the I p x prime minus x over h bar. And once again, that's equal to the delta function, according to the first integral we did today, we talked about today. Okay, so that works as a check that everything's okay. Another question we can ask is, suppose somebody gives us a wave function in x, what's the wave function in p? So given psi of x, which by definition is this, x psi, what is psi tilde of p, which by definition is p with psi. Okay, what else should we do? By now you know that the only thing to do is use completeness. Okay, and so psi tilde of p, by definition, is p psi. We're going to do an integral over x of px x psi. Okay, this is psi of x by definition. This is phi p of x by definition. And so we just plug in what those things are, and we get 1 over square root of 2 pi h bar, integral minus infinity to infinity dx, e to the minus I px over h bar, psi of x, which is, by the way, the Fourier transform. So that's saying the answer to the question of how you get the momentum wave function given the position wave function, you take the Fourier transform, where our physics definition of the Fourier transform involves these h bars in strategic places. Conversely, you could ask the opposite question. Okay, and so psi of x, given psi tilde of p, we can get by just doing the analogous thing. Now we're going to use completeness in p. Okay, so it's always just a matter of figuring out, should I use completeness in p or should I use completeness in x? Okay, but in this case, it's 1 over the square root of 2 pi h bar minus infinity to infinity dp e to the positive I px over h bar psi tilde of p, which is the inverse Fourier transform. Which makes sense because we did the inverse operation. In one case, we found psi tilde of p given psi of x, and then secondly, we found psi of x given psi tilde of p. Okay, what else can we do? We can take matrix elements. So for example, suppose we consider x the operator with psi. That's equal to x times psi of x, because the x operator acting on the eigenket x is just x. And similarly, if I do x p psi, that's equal to minus I h bar d by dx of psi. That's by the definition of the p operator. So the way we say this is that in the x basis, or in the x representation, the operator x is represented by the number x, and the operator p is represented by the operation minus I h bar derivative. Okay, and then similarly, I can consider the matrix element p x psi, and that's I h bar d by dp of psi tilde of p. Whereas, if I consider this matrix element of the p operator in between the same two states, that's just the number p times psi tilde of p. Okay, and so we can summarize that by saying in the p basis, what those equations mean is that the operator x is represented by I h bar derivative, this time with respect to p, whereas the operator p is related to or represented by just the number p. Okay, and so for example, of using these things, suppose instead of looking at momentum and position eigenkets, I look at any two kets, psi 1 x psi 2. So you can show using completeness, this is integral over x from minus infinity to infinity of psi1 of x star, psi2 of x multiplied by x. But it's also equal to an integral over momentum if I use momentum completeness. And so this would be psi1 tilde of p I h bar d by dp of the momentum wave function for the ket2. Like so. And then I can do the same thing for the momentum operator. This is, if I use completeness in p, I get an integral over p, and it works out to psi1 of x star minus I h bar d by dx, psi2 of x. Or I can write it using position completeness as minus infinity to infinity dx. Oops, this was a position completeness. And this should have been a momentum completeness. I got my completenesses mixed up. Of psi1 tilde of p, p psi2 tilde of p. And I'm missing a complex conjugate here. All right, so that's all we have time for today. Oh, one thing I should mention is that you should have all received your homework ones back. I should have emailed them all to you. If you didn't get homework 1 back, let me know and I'll try to figure out what happened, or you can check your spam folder. Also, homework 3 was out on Wednesday. So you should always check the course webpage to download the new assignments. So it's on the course webpage and you can download it, and that's also due as usual this Wednesday. Okay, so I will stick around to answer questions as long as anybody has any. But that's it for today, and so everybody have a good weekend. So I'll stop the recording now.